Hello and welcome to this new series of videos on vector space math. In this first video I would like to explain in more depth some parts of it which were overlooked, neglected and given next to no attention, like for example these little vector space theorems such as 0 times u equals 0. These three theorems I've written here look painfully obvious. Why would such a theorem need such a proof, since we've all taken it so much for granted that these things are all true? The proofs that were presented were nasty and overwhelming. Well, firstly, in the first theorem, the 0 on the left-hand side is a number, and the 0 on the right-hand side is a vector, like the letter U. So it isn't just a plain 0 times something is 0, like in high school algebra. There are theorems and there are axioms. Axioms are the very obvious things that you can say are very obvious and can take for granted, while theorems are more obscure and need to be proven by the proper use of the axioms. It's just like stepping stones in a pond. With the axioms, the stepping stones are close enough so that you can just step across easily. But with the theorems, the stepping stones are too far. So you have to use a lot of little steps, axioms, to get to the stone that's far away, the theorem. The accumulation of little steps may be thought of as the proof. We're firstly going to prove that 0 times u equals 0, and we'll call it Theorem 2.4.1 based on the textbook I'm using. The proof uses the other vector space axioms which are assumed to be true for any vector space. This proof is quite over-abstract for most people, but with a little rearrangement and careful explanation, it can be more easily understood. There is quite a story to it, as it turns out. So there are three things that I would like to do differently so as to avoid all the confusion and messiness that come with these proofs. The first is to rename all these variables. 0 will be renamed to z, so that it will be very clear that the 0 of a vector space is very different to the number 0. And so as to more easily follow the proof. Minus u will be renamed n for negative. I always found minus u to be even more confusing and misleading in vector space proofs than 0. A second thing I'd like to do is give the different variables their own colours, so as to make them easier to see and keep track of. U, Z and N are vectors, while C is a constant or number. I think that the particular colours that I give them convey their character too. And lastly, I'd like to change the form of the proof, so that it will start with the left-hand side of what we're trying to prove, and end with the right-hand side, making the proof easier to follow and understand, which isn't normally done with this sort of proof. And before we start, I'd like to give you a look at what these vectors look like in more detail. They are strings of numbers in a row or column, but u, n and z must contain the same amount of numbers to be in the same vector space. The amount of numbers in these vectors can be any positive integer, 1, 2, 3 and so on. They can even have an infinite amount of numbers, as in the case of an infinite vector space. This is the main reason that we'll prove this theorem the way we're going to do it, because using normal vector addition and multiplication of each number in each vector doesn't work in the case of an infinite vector space. It might be a good idea to take notes so as to let the lesson sink in, because it is something that most people aren't used to. It is also a good idea to watch it once a day over 5 to 10 days, just to get used to it. And so to begin the proof, we write out the left-hand side and try by a number of steps to evaluate it to the right. starting with 0 times u, and supposing that u can stand for any vector in the space, we use the property of 0 to expand it by adding a z vector onto the end. Notice that this axiom is run in the reverse direction to which people are normally used to using it. We never expand an expression by adding a 0 onto the end. We only simplify it by getting rid of the 0. But in order to prove this theorem, it is necessary to use a number of expansions so as to get to an expression that we can manipulate and then simplify to get the right-hand side and successfully prove the theorem. The next step is to expand the 0 into a vector and its negative, which is the property of the negative of a vector. This again is used in the reverse direction to which people are commonly used to using it. U and n can be written in any order, u plus n or n plus u. So we've strategically put the u first because we need the two expressions containing u to be next to each other. So this is the line where we do the main manipulation of the fully expanded expression. We've invoked the associative law of addition so as to swap the brackets. It doesn't look like much here, but as we continue to simplify the expression, it will slowly become clear just how important this step is. Here we've invoked the property of the number 1. It is another expansion and could have been done before the line preceding it. Sometimes the proof doesn't have to be in an exact order in some places, but usually has to be everywhere else. It is a very important step, so that the next step can be done, which is very strategic. And this next strategic step is to invoke the distributive law of addition and group the numbers 1 and 0 together. This looks like factorizing in high school algebra, and it is helpful to see it like this. The order has to be preserved, however, and can only be changed once the numbers have been grouped together as is shown. The next line is to add the 1 and 0 together to make 1. This line has to be put in because the invocation of the next axiom depends on it. Notice that they can only be added together once the numbers have been factorized. In this line, the property of the number 1 is used once again, and this time in the order that people are used to using it, to simplify it. Notice that after the expansion and manipulation, that the expression is starting to turn into something entirely different from what it was. And now we invoke the property of the negative, adding u and n together to make z. This is using this property, this axiom, in the order so as to simplify the expression. And behold, the theorem is now proven. We have shown by a series of steps that 0 times u equals the 0 vector. If this proof is a bit too much to take in all at once, then it might be a good idea to watch it once a day over 5 to 10 days until it becomes familiar. Now that we've completed the proof, we can draw the customary black square. Here are the parts of the proof where expansion and simplification take place. It needs to be expanded from the beginning until, in the middle, it is manipulated into something else, and finally simplified into something different from the beginning. Here is an alternative path for the proof, since we can invoke the two axioms in a different order in this section. And we can use this theorem to prove another theorem, because now that it has been proven, it has the strength of an axiom. We can use it to prove that minus 1 times u is equal to n, or the negative of u. Notice here that this proof looks identical to the previous proof in every line, except that we've replaced 0 by minus 1. But in this last line, we will invoke the theorem that 0 times u equals 0. And now, having invoked it, we now have an expression that looks obviously like it could become n and so complete the proof. But we must be careful and still invoke the property of the zero axiom. Yes, we have invoked the property of zero axiom, and so we have completed the proof. Now we know with certainty that -1 times u is equal to the negative of u. But it was necessary to use the theorem that 0 times u is equal to 0. As a note, this isn't the way that these proofs are presented in normal lessons, so it isn't a good idea to display them this way in exams. If you're going to, however, at least define what z and n are before you start. And now to prove this theorem that any number multiplied by 0 is equal to 0. This is different to the other zero theorem in that now both zeros are the zero vector. It uses the other zero theorem in its proof. And remember, C is a number and not a vector. I'd like to stick with the convention of using the following form of proof. That is, to start with the left-hand side and use a series of axioms to transform it into the right-hand side. I'd like to stick with these new variable names like z and n and to have them coloured in. And in the first line of this proof, we use theorem 2.4.1 to transform the vector z into 0 times u. Notice too that I've used this theorem in the reverse direction so as to expand the expression. And in the second line, I've invoked the associativity of multiplication axiom so as to swap the brackets. This sets us up for the next very important step, which is to multiply c by 0 to get 0. Since they are both numbers, I don't need a vector space axiom here. Here is a list of possibilities of what c could equal. It is even possible for it to be the imaginary number I. And now we use theorem 2.4.1 in the forwards direction so as to simplify the expression to be z. And so now we've completed the proof in only 4 lines. Now to prove that this expression is true, notice that it is not the same as 1 plus 1 equals 2. In the first line, we use the property of numbers to expand the expression from 2 to 1 plus 1, which is a reverse process with numbers, so that you can manipulate it in the proof later on. And now we use the distributivity of addition in a direction so as to expand the brackets. It can be thought of as a simplification, even though it isn't a factorization. And now we use the property of number 1 on both u's to get this expression. And so this completes the proof in only 3 lines.